We're going to start with chapter 2 today. We will learn about the limits and the derivatives. Section 2.1, the tangent and the velocity problems. So our goal in this section is how does the limit arise when we attempt to find the tangent to a curve or the velocity of an object. So when we say tangent, this is from the Latin word which means it's tangent, and the tangent means it touches. So the line which touches the curve at one point is called as tangent. So here's the formal definition of tangent line. A tangent to a curve is a line that touches the curve and it has the same direction as the curve at the point of contact. Suppose I have a curve here and say this point here on the curve, I have a line which touches the curve, and this line is called as the tangent line. Example 1. Draw a tangent line to the given parabola at the point P of 1, 1. So first you want to draw a parabola y equal to x square. This is the y equal to x square parabola. Now say this is 1 on the x-axis and say 1 on the y-axis, which means this is the 1, 1 point. And you want to draw a tangent line at 1, 1. So you draw a line which touches the curve at 1, 1. And you call this line to be the tangent line. Next is application. Suppose that the ball is dropped from the 5th floor of a building 450 meters above the ground. Find the velocity of the ball after 5 seconds. So we have a recall. This is by the Galileo's law that the distance after t seconds is given by this formula, where v sub 0 means the initial velocity and a is the acceleration. So let's start by calculating the distance d, and the first plug-in will be 0, and then you have plus 1/2, acceleration is 9.8, and the time t square will be t square itself. To start with, the initial velocity v sub 0 will be 0. And then you simplify, you have 4.9 t square. So you have distance, which is a function of time, so it's d of t, 4.9 t square. Next, it's hard to find the velocity at a single instant of time t equal to 5. So with the only distance given, so thus we will use the average velocity formula, change in the position divided by the time elapsed. So it's distance at 5.1 minus the distance at 5 divided by 5.1 minus 5. So this is 4.9 times 5.1 square minus 4.9 times 5 square. We derived a formula for distance on the top in the first part of the problem, which is 4.9 t square. So we are plugging in t as 5.1 and 5. Denominator, find the difference as 0.1. Simplify this expression, you get 4.49.49 meter per second square. Next, you have given a table. The following table shows that the results of a similar calculation. We note that as we shorten the time period, the average velocity is becoming closer to, let's read this, Now the starting interval is 5, 6. You see the interval is reduced 5, 1, 505, 501, 5.001. So as you reduce the interval, I want you to observe the average velocity. It's going down. And the last three values are showing that it's converging to 49. So you might want to write here that this is becoming closer to 49 meter per second square. Next is instantaneous velocity. So when time t equal to 5, the instantaneous velocity is defined to be the limiting value of these average velocities over the shorter and shorter time periods that start at t equal to 5. Thus you want to say the instantaneous velocity after 5 seconds is 49 meter per second square. Next is connection between the tangent problem and finding velocity. So first we want to draw the graph of the distance function of the ball and consider 2 points. So I want you to draw a graph, a smooth curve to start with. Name 2 points on the curve P and Q and draw a secant line which touches the curve at these 2 points. Now drop a perpendicular from Q and drop a perpendicular from P and join these horizontal line Mark the first coordinate as A, the second coordinate is an increment of the first coordinate, so A plus H. And you want to understand the smooth curve here is the distance function, which is the 4.9 t square. D equal to 4.9 t square. So first draw the graph of the distance function, which we draw of the ball, and we are considering 2 points, P and Q. In general, suppose the points you consider P and Q are defined as x1, y1 and x2, y2, and say I want you to find the slope of the line. You know slope is rise over run, so it's the subtraction of y coordinates divided by the difference of the x coordinates. Now we all know that the distance function is 4.9 t square. So I want you to write here the slope of the secant line is same as the average velocity. I want you to also name the coordinates here. Coordinate P is A 4.9 A square and coordinate Q is A plus H, the coordinate which is moved, and it's 4.9 A plus H square. So when you calculate the second set of coordinates in this P and Q, which is x1, y1, x2, y2, when you calculate this y1 and the y2 coordinates, you will be using the function definition, which is d of t equal to 4.9 t square. So when you calculate the value at a, you will plug in d at a and you get 4.9 a square. Since at a plus h, you will plug in a plus h, so you get 4.9 a plus h the square. Now you're trying to define MPQ, which is the slope of the secant line PQ. It's the difference of the y coordinates minus the difference of the y coordinate y sub 1 divided by the difference of the x coordinates. So I want you to write a note on the secant lines here. As soon as we say secant, this is again from the Latin word secant, and this means cutting. So here the cutting means a line cuts the curve more than once. So in the second note we have MPQ is same as the average velocity over the time interval a and a plus h. Therefore, the velocity at the time t equal to a, the limit of these average velocity as h approaches 0 must be equal to the slope of the tangent line at p. So we have the definition here. Now the smooth curve, the 4.9 t squared, the distance curve, I'm going to have just one point here P, and I have a straight line here, which is the tangent line, which touches the curve exactly at one point, and say the drop down perpendicular distance is A, and say the h, the small increment in the x value is approaching A. So you're not seeing the value Q, and you're not seeing the a plus h coordinate. So now we're going to define the slope of the tangent line as the instantaneous velocity. In the next example, the displacement of a particle moving back and forth along a straight line is given by the equation, where t is measured in seconds. You want to find the average velocity during each time period. So you're given the interval is 1 and 2. So you want to write V average, which means V for velocity, AVE for average. Average velocity is given by the formula S at 2. S stands for the distance, minus S at 1 divided by the time values 2 minus 1. So you know that S is 2 sine pi t and so on, which means this S here you have to understand as a function of t. You want to find S at 2. So you write 2 sine pi 2, you're plugging in t equal to 2 in the given expression for S. And then you have 3 cosine pi 2. Then you have negative. At 1, the value is 2 sine pi 1. And then you have 3 cos pi 1. Now you can put brackets, understanding that negative is common for both. Denominator simplify, you have 1. You have to make a note of the trig values, which you will be using often when you see a trig expression. Sine of n pi is always 0 for n equal to plus minus 1, plus minus 2, and so on for all the integer values. So whenever you see a sine pi 2, which is a sine 2 pi term, or a sine pi term, you can say that these values are 0. Similarly, you want to remember a cosine expression value. Cosine n pi is generally written as negative 1 to the n. If n equal to odd, cosine n pi will turn out to be negative 1. If n is even, the cosine n pi value will always be positive 1. So here you have cosine 2 pi and cosine pi. Cosine 2 pi is going to give you positive 1, whereas cosine pi is going to give you a -1. So simplify, you have 3 negative of -3 divided by 1, it's 6, and the unit will be centimeter per second square. This is given in the problem. In the next part, you are asked to find the average velocity for the interval 1, 1.1. So you do a similar formula, V average S at 1.1 negative S at 1 divided by 1.1 minus 1. Simplify S at 1.1. This is negative 3.471. Negative of -3 divided by 0.1. Simplify, you have negative 4.71. The next one, 1.01. Similarly, calculate the V average. S at 1.01 negative S at 1 divided by 1.01 minus 1. When you simplify, you see that you get negative 6.13. The next one is 1.001. So the V average will be S at 1.001 negative S at 1 divided by 1.001 minus 1. Simplify, you have negative 6.27. So we are reducing the size of the interval. Say it was from 1 to 2 to start with. We choose 1.1 and then 1.01 and then 1.001, which means we are making the interval smaller and smaller, and then we are calculating the average velocity expression value. So when you make the interval smaller and smaller and say the value of t is approaching 1, this is your definition for instantaneous velocity. So question asks you to estimate the instantaneous velocity of the particle when t equal to 1. We started with 6, we got negative 4.71, negative 6.13, negative 6.27, and so on. So now you want to write the instantaneous velocity when t equal to 1 appears to be about negative 6.3 centimeter per second. So we'll end this section here.